Okay, so in the previous video, we saw the driving forces, which again, the main driving force was going to be the weight of the material, right? The weight of that slope material is going to be the main driving force for moving things down slope. Now we need resisting forces. So resisting forces are those that oppose that downslope movement. So the main resisting force is going to be shear strength of that material. So if it does move, it usually tends to move within this slip plane. So if you think of a slide or a slump, whenever those surfaces on top of which the material would, slide down or slump down, is because the shear strength of the material is too weak. It's not strong enough to support that movement, or that weight, I should say. That is the driving force. So again, if it does move because the shear strength is not enough, then that is going to move through these slip planes, which are going to be breaks in that consistency of the material. So that is why, for example, the boundary between the bedrock and the regolith is such a good place for the whole material to move down from, because there is a break in the consistency of the material. The bedrock is very cohesive, obviously solidified, and then everything on top is pretty much sort of unconsolidated material. So there is a break in that consistency. So vegetation actually acts kind of both as a resisting force and a driving force. So remember that driving forces want to move things downslope, resisting ones opposes that downslope movement. So it's pretty, I guess, easy to imagine vegetation as being a resisting force because it gives more consolidation to the soils by acting, as roots on the soils are going to make them more consolidated. So it's easy to think about it as a resisting force. It's going to oppose, the main downslope movement. It's also going to decrease the amount of moisture in the soils by using that moisture in the soils. So that's going to help, not weaken the slope itself. However, it sometimes can be a driving force. So because vegetation itself is so heavy, if you have a spring, for example, that is incredibly moist, and not enough moisture in the soils can be absorbed by the vegetation, then if the soil is saturated enough and you have a lot of weight added due to the vegetation, then the whole slope may completely loosen and slide downwards. So vegetation can be a resisting force at certain times, but it can also be a driving force at other times. So when we are trying to determine that slope stability, we use something called the safety factor, or the factor of safety. This factor of safety, or again safety factor, otherwise known as SF, is going to be the ratio of the resisting forces over the driving forces. So again, if you have resisting forces being greater than driving forces, then the safety factor is going to be greater than 1. If you have driving forces being greater than resisting forces, then the safety factor is going to be less than 1. So you can think of it as a balance kind of example. So again, if resisting forces are greater than driving forces, then the safety factor is greater than 1, which makes that slope stable. Okay? And then if the driving forces are greater than the resisting forces, the safety factor is going to be less than 1, which makes the slope unstable. Okay, so stable is greater or equal to 1, and unstable is going to be less than 1. So what factors do you think affect affect the slope forces to make an area more prone to landslides? I'm going to let you think about that for a minute. So there are quite a few factors, so we're going to go through them now. One of those is going to be the earth material type itself. So it's going to be based on mineral composition, and not just, for the most part, you're not just going to get a monomineralic composition for these earth, but it's going to be a multiple mineral kind of composition. But let's give the example here of just one single mineral composition. So you get the idea. So on the top, over here on the left, we have micas, which are in this case they're muscovites. So you see that they form as one single kind of sheet, one single plane, and the hardness is not very great. I think the hardness on a muscovite is about 2 to 3 in the mole scale, so not very great. And then the chemical structure, as you are seeing there, kind of shows you that they're gonna cleave into one single plane. And then on the bottom we have quartz. So quartz over here is going to form, because of its crystal structure, is going to form as these kind of arrays in which they don't form as one singular plane, but it's going to form kind of like, it's not cubic structures, but it's more like lumpy bunch of complex arrays, if you would, of atoms. And so it's not going to have this nice planes, but rather it's going to have this kind of consolidated chunks. So quartz, for the most part, is going to make this kind of granite, as we see in the Idaho batholith, is one of the big minerals that is common in granite. And then this muscovite makes up this very flaky kind of shale material that we're seeing in the top image. So which of the two do you think is going to be a material that is easier for slides to occur in? So if you're thinking is the muscovite, the mica material, you're correct. So as you're seeing here, first of all, it is singular plane. Second of all, it's not very hard. Third of all, it's going to have a lot of pore spaces within the material that it forms. So it's going to allow for a lot of water to reside in. However, quartz, because it's so well consolidated, and it doesn't have that weakness, is very strong, very hard, is going to, and it doesn't have very much pore spaces either, is going to, allow the material to have a lot more force to resist any sort of downward movement. Okay, so how are each of these different materials going to affect whether I get a rock fall, a slump, or a slide, for example? So soil slip is really more like a slide, is what they mean there. And so that has to do both with consolidation of the material and the cementation of it itself. So we know that a rockfall occurs when I have unconsolidated material that forms this cliff. So it could be unconsolidated material, but it could also just be, oh boy, give me a second. But it could also be just full-on bedrock that is forming these cliffs, as we're seeing in the image on the right. Maybe, there you go, on the image on the right. So again, most of these rock falls occur because of that frost wedge, frost thaw, I guess, action from the weathering cycle of freezing and thawing. So that's where we would get those. The slumps, on the other hand, are going to be unconsolidated weak material that is flowing downhill. So it's going to be more like mudstone all throughout the weak material that is flowing on top, and also tends to be kind of weak material on the bottom. But for whatever reason, it's still a little bit stronger than the material that is flowing on top. So for the most part, slumps, although they do occur at some sort of curved surface of weakness, that surface of weakness tends not to be the bedrock, but simply another material underneath. And then the soil slip, or the slide in this case, which is what they mean, is going to be that unconsolidated material over the bedrock. So remember, it's everything that's the regolith, so that unconsolidated material that usually slides past this plane, separating it from the bedrock underneath it. Okay, so again, that is where our earth material type is going to have a big effect. If I have a material that is made out of muscovite, as we saw in the previous slide, it's for the most part going to be unconsolidated, or even if it is consolidated, it's going to be very easy to break. It's going to be very weak. However, if we have a material that is consolidated and hard like quartz, then it might only be propense to things like rockfalls, where I have that frost wedge action taking place. Okay? My computer just kind of went crazy, guys. Sorry.